previous class, we already showed you what is the Rayleigh mechanism and what is the vacancy mechanism. So let's move to the third part, which is the interstitial mechanism. Okay, so what is the interstitial mechanism? We have the host atoms, right? And interstitial mechanism means we have a solute, small solute atoms, and moves through interstitial site. And due to if the smaller solute atom want to jump from this interstitial side to this interstitial side, then you can expect it for sure there's a lattice distortion happen. So this interstitial atom need to have sufficient energy to overcome this energy barrier, which is the related or depending on the lattice distortion energy. So the only energy this solute atom need to overcome is this migration energy, highly related with lattice distortion energy, right? So we can express this the facility of this smaller solute atom like this. The first term D0 is the temperature independent term, and the second term is a temperature dependent term. And inside this exponential term, the delta H is only included the migration energy of these interstitials. So next I'm going to give you some information about the interstitial side. If we take the BCC as an example, if we have an interstitial diffusion happen in BCC structures, then we have two different types or kinds of interstitial site. The first one, figure A, is the octahedral interstitial site. As you know, this is the BCC structure, right? We have the 8 atoms at the corner and 1 atom at the center of this cubic. We call it BCC. And we use a smaller white ball to represent the octahedral interstitial site. So what's the octahedral interstitial site? If you take this atom, this interstitial site and as an example, this position actually is located at the center of this octahedral structures, right? It's at the center. And the figure B represents the other type or kinds of interstitial site. We call it a tetrahedral interstitial site. And as you see here, this interstitial site is at the center of this tetrahedron. This tetrahedral interstitial site located at the center of this tetrahedron structures. So there are two different types of interstitial site in BCC, and if you try to Google or check the interstitial sites in FCC, you also can find there are also two interstitial sites, which are the octahedral interstitial and tetrahedral interstitial site in FCC. Okay, so next, as we mentioned before, we want to try to formulate or derive the diffusivity of these interstitials. Right? So the example here we talk about and we show you is a BCC. We have a material with BCC structure, and it is a interstitial diffusion. So here, the interstitial site we talk about here is focused on the octahedral interstitial site. So first of all, you need to draw a single cubic of BCC, then mark all the octahedral interstitial site as we show here white ball or white circle. And next, because this is interstitial diffusion happens, right? So based on the equation we derived from previous section, diffusivity equals to total jump rate, mean square jump distance divided by 6 times f, right? So we need to figure out what's the z, what's the small r jump distance, and also the f. So in order to simplify these structures, we draw these figures to demonstrate, to show you how to determine the z, the coordination number. If we focus on this phase, this plane, and we focus on the interstitial side at the center of this plane, and there are 4 possible jump directions to these interstitials, right? Because they all list 4 also the arthahedral interstitial side. So based on this concept, we know z equals to 1, 2, 3, 4, 4. And the distance, the small r jump distance, equals to a divided by 2. 1, 2, 2. You got a small r. And because it is interstitial diffusion, so as you know, your solute atom at the interstitial side can jump to any interstitial side. This jump is nothing related to previous jump or next jump. So f equals to 1. Okay, so here z equals to 4, 1, 2, 3, 4. And so here when we try to formulate the diffusivity of these interstitials or these solute atoms, show us the 4 gamma prime small r square, so we got square, and f equals to 1 and divided by 6. And next we just organize the temperature independent term here, and temperature dependent term just copy here. So you can express the diffusivity as d0 times the exponential temperature dependent term. Okay, so now we successfully to formulate the diffusivity of this solute atom located at the interstitial side. I want to explain more about, some students ask me about, Professor, can this solute atom at this arthahedral interstitial side jump to here? Instead of jump here, it's possible to jump here? If you calculate the distance between these two interstitial sides, this is longer than this distance, right? Between this, right? Don't forget, when you determine the jump distance, direction, and also the distance between two interstitial sides, just need to figure out the shortest jumping distance has a higher possibility to allow this interstitial to jump to. So we just consider the shortest location or site. So for this interstitial site, there are only 4 nearest interstitial site nearby. And this one for sure is longer than this one, right? And the other thing is, some people probably will ask about, Professor, as you mentioned in previous slide, there are 2 different types of interstitial site. How can we control the diffusion of these interstitials only jump through arthahedral interstitial site? Is that possible to control this? No. It is not. You cannot just control the interstitials only jump through arthahedral interstitial site, because regarding to what types of arterhedral what type of interstitial site, what kind of mechanism is either this interstitial is through arterhedral or tetrahedral interstitial site, will depending on the energy, okay, the migration energy of these interstitials. So in most of case, in real case, I will say the interstitials in most of case will jump through arterhedral interstitial site compared to that through tetrahedral interstitial site. But it's impossible to 100% of interstitial just jumping through arterhedral interstitial site, or 100% of interstitial solute atom jump through tetrahedral interstitial site. But you can roughly think about, you can just roughly, based on the energy point of view, which energy will be lower, then that will allow interstitials to jump through. Okay, so but some student ask me, but in this case, we assume in order to simplify and in order to easy to estimate the differentiability of interstitials, the questions usually will make some assumptions. For example, that these interstitials jump through arterhedral interstitial site. And under this situation, you get the diversity of these interstitials. Just simplify the questions and can help you to easily to estimate the diversity of this interstitial. But don't forget, in real world, we cannot totally well control your interstitials jump through 100 jump through arterhedral interstitial site or 100% jump through tetrahedral interstitial site. For sure, it's a portion, a ratio between them. Okay. And next, I'm going to show you is the examples. So, for example, like if I have iron materials, and I try to dump the smaller carbon atom inside these iron materials. And after calculation, the size of carbon is smaller and can be located at interstitial site in iron structures, crystal structures. So what's the D0 and migration energy of these carbon atoms? So first of all, you need to make some descriptions. For example, like due to the size is small, the size of carbon is small enough. So I will say when you try to dump carbon into iron materials, the carbon for sure will diffuse through interstitial diffusion mechanism. So based on this, how to get the D0 and migration energy? So based on these results, I would say if you can measure the diffusivity of the interstitials, means the diffusivity of the carbon atoms at different temperature, then you plot log di versus 1 over t, then you will get these figures. So I measure the diffusivity of carbon at different temperature T1, T2, T3, and T4, and plot this log D as a function of 1 over T. Then you got this for data point, right? So right after fitting, then the slope will be equals to minus E divided by KB. So you can easily get the migration energy from the slope. And regarding to the intercept of this figure, then you can get as long as you know fitting, right, you get the log D0 equals to this value, so we can calculate the D0. So this is how we determine the D0 and migration energy or enthalpy. of the carbon materials in the iron materials. Carbon atoms diffuse through iron materials. So based on these results, we can, from the experiments, we know D0 expressed like this equals to this, and migration energy equals to this. And just a quick remind, in some figures, some people will use R, and some people will use the KB. The difference just between the energy, the unit of energy you use in the upper portion. For KB, the energy here, the unit for of energy, migration energy here will be talking about per atom, but here will be per mole. So please check the unit while you answering the questions, okay? So this is the experimental results. Then how to estimate the D0 and migration energy? Do we have chance to estimate that? Regarding to D0, we can do some estimation as long as we know the A, mu, and migration entropy, then we can do that. So either you can, for lattice constant, you can check from, you can either check from literature or measure that from the XRD, then you can get the lattice constant of these materials. And mu and entropy, you can check from the literature. Then based on this data, we know the D0 equals to this. So compare the estimation, the results between the estimation and experimental results. The results are consistent, right? So which implying that by performing the experiments, we have chance to correctly or accurately estimate the D0 and also the migration energy or enthalpy of your materials. So this is the diffusivity of interstitials. This is how we this is regarding to the diffusivity of the interstitials, right? And how we get these results actually is based on the equation we derived from first section. But some people probably will ask about, Professor, actually we learned last information from the fixed first law, right? And this diffusion, the interstitial diffuse through crystal, this kind of stuff, can we get the diffusivity through the fixed first law? Fixed first law means the flux equals to minus diffusivity concentration gradient. Because if you can expect that the solute atom diffuse through crystal, right? Through interstitial side inside crystal. So can we have the other approach to get the diffusivity by using the fixed first law? So next I'm going to show you how we can get the diffusivity by using the fixed first law instead of using the equation we derive from first section. So the idea, before we move into the detailed derivation, the idea will be that what's the fixed first law would be the net flux passing through this net flux of diffusing atom passing through this BCC equals to diffusivity of these interstitials concentration gradient. So we assume there's a constant flux of diffusing atoms passing through along y-axis. So this is a fixed first law, right? So the idea would be that if I can find, then and this is a cubic we are interested in, is a BCC. And if I identify this is alpha plane and this is beta plane, in order to get the net flux, so I define two planes, alpha and beta. So if I can formulate the flux from alpha to beta and minus the flux from beta to alpha, then I can get the net flux by J alpha beta minus J beta alpha, then I can get the net flux along y-axis. As long as I get this one and express as in terms of concentration gradient, partial C, partial Y. Based on this, then I can compare these results with Fick's first law. And the rest of part will be the diffusivity of these interstitials. Because the rest of part are the same, right? So the idea will be that. So our purpose, based on this idea, the purpose here is we need to formulate the flux from alpha to beta. So the flux of interstitials moves from alpha to beta. Okay, so this is the idea. So our material actually now is a BCC structure, so I use the blackboard to identify the unit cell of BCC. We got the corner and one at the center. And because this is interstitial diffusion through octahedral interstitial site, so I use this cross symbol to represent the octahedral interstitial site. For the alpha plane actually is here. You can see that the blue cross actually is the interstitial site at the corner, and the orange cross means the interstitial site at the center of the plane. Center. And regarding to the beta plane, I use a green cross to represent this 1, 2, 3, 4, 5, this 5 interstitial site, and 4 at the center of the edge, and 1 at the center of the plane or on the center of the face. So now we tell you we already highlight all the interstitial site on alpha plane and beta plane. So next I'm going to show you how to get the flux, net flux from alpha to beta, net flux of interstitials, okay, and at the interstitial site. So first of all, we need to try to link the flux with the atomic jumping behavior. So what's the unit for flux? Will be the numbers of atoms per unit time and passing through per unit area, right? So it's based on the you can rewrite the flux equals to total jump rate times the area density. Then let's do the unit check. Is the numbers of atoms passing through unit area and unit time the same unit, right? So the flux can be rewrite as equals to gamma total jump rate times area density. So based on this relationship, we try to calculate the flux of diffusing atom interstitials from alpha to beta. Okay, and the C-prime, don't forget, is area density of interstitial solute atom in the alpha plane. So it's area density of interstitial solute atom in alpha plane. And as you know, it's an interstitial site, right? Area density of interstitial site. So for the blue one at the corner, if you consider area density is a quarter, right? A quarter, so you got 1, 2, 3, 4. You got the 4 times a quarter. And plus what? You also have orange. Orange is at the center of the face or of the plane. So it's a half, right? You got 4 times half. And this is a total number of the interstitial site divided by area A times A. So this is area density of interstitial site. It's 3 divided by A squared. So this is C-prime. And now my question here is I need to know the flux from alpha to beta, means this area density, this interstitial site. If the solute atom locate at this interstitial site, which solute atom can make a successful jump to beta plane? That's quite important, right? So that can help us to identify the J alpha to beta. So based on this, I will ask, if the solute atom locate at or sit at this interstitial site, can either make a successful jump to beta plane? No, right? Because there's an atom locate at this edge. So if I have a solute locate at this interstitial site, it cannot make a successful jump to beta plane. The same happen on this interstitial side, this interstitial side, and this interstitial side, right? It cannot make a successful jump. But if the solute atom locate at this interstitial side, it can make a successful jump to beta plane. And the distance is what? Is 2 divided by, or A divided by 2, right? But some people probably, this one also can make a successful jump, right? This also. But some people probably at this moment will ask, yes, professor, this if solute locate at this interstitial site can make a successful jump to beta. But how about this? If solute locate at this interstitial site, why it cannot jump to beta plane through this jump from blue cross to green cross? The reason is this one is longer than this distance is longer than this one. So as I mentioned before, the atoms always jump by the nearest distance. Okay? So based on this, we know we have 3 atoms, right, in total, and only this orange interstitial site can allow the solute atom make a successful jump to beta plane. So this blue atom, if you calculate, is a 4 times half. So it's a 2 atoms in 3 atoms. 2 divided by 3, you got a 3 total, and only 2 atoms, 2 interstitial site can help the interstitials to make a successful jump to beta. So based on these descriptions, we can formulate the J alpha to beta would be like, the first one is total jump rate. So you need to consider the jump directions. So directions actually is all the way to the right? And these direction is a vector, right? These directions are parallel, so just one directions times the gamma prime. And the second term is regarding to the C prime's area density. Not all the atoms at not all the interstitial site on alpha plane can help the interstitial make a successful jump. Only 2 in 3 interstitial site can help the interstitial make a successful jump. It's a 2/3 C prime. So we got these results. It's 2/3 gamma prime C prime. And next, don't forget C prime. What's the unit for C prime? Is the area density, right? But if you take a look on Fick's first law, what's the unit for C? Is it the area density? No, it is a volume density, right? So we need to, finally we need to compare with Fick's first law. So we need to convert this area density into volume density. So how to do that? We need to, this is a plane, right? We want to convert this plane to a volume. So I give you divided by a distance, right? So let's divide volume for this interstitial side. So if So I will choose this distance h/2 to allow this interstitial area density to become a valence density of this interstitial side. Because when I choose this valence, the total numbers of atoms remain constant, and also this valence do not involve extra interstitial side, and also this valence is duplicate, right? It can be duplicated. So we just use C prime to divide it by the length of this valence, so divided by A/2. So we use C prime equals to C times A/2. So we use this to substitute C prime. So you got the flux from alpha plane to beta plane equals to A divided by 3 gamma prime C. Now C is the same unit with the fixed first law. So we successfully got the J alpha to beta. Next, we need to calculate the J beta to alpha. Some people probably will follow the rule I just showed you, right? Calculate the available C prime is 2 is half. So this is half 2 and 1, so it's 3 atoms the same, right? Divided by I squared, and calculate the possible jump directions and determine whether each atom can make a successful jump. Obviously, this solute atom at this interstitial site cannot make a successful jump to alpha plane, right? But if you follow this rule, then the results, the flux from beta to alpha, you can get the value for that. But don't forget, the net flux, you use this value to minus a value, then you cannot get a concentration gradient term. So you cannot compare with fixed first law to get the DI. So based on this reason, you know that J beta to alpha will express in the other approach. The other approach actually we change the C. We copy the 3A gamma prime and the C, the concentration part, to describe the beta on the interstitial concentration on the beta plane. We use the C, the concentration in valence concentration in alpha plane, plus the A/2 partial C partial Y. It's just a first order approximation. So use the partial C partial Y, right? And times dy. Dy is this one, right? So it's A/2. So you got the successful got the flux from beta to alpha. So use this term to minus this term. So the only one you left is this term times this term. So we got these results. So based on this trick, so you got a concentration gradient along y-axis. So you can successfully, after compare with fixed first law, so you got the diffusivity of these interstitials equals to this value. Okay, and some people want to convert it gamma prime to gamma. So don't forget, the gamma prime to gamma, you need to back to the structure point of view to determine Z equals to 4. It's not equals to the one you just derive from fixed through this deviation. The Z equals to the one you need to calculate the coordination number for this interstitial side. So it's Z equals to 4. It's 1, 2, 3, 4, right? And some people also want to convert it A into R. So A equals to 2R. So you can just convert it to express the diffusivity in terms of R and gamma. Okay, So this is how we get the diffusivity of interstitials through Fick's first law flux solution or solutions for derived from Fick's first law. So next I'm going to give you an examples. But the crystal structure we talk about instead of BCC, now we talk about is FCC. So now we consider an FCC structures and lattice constant is A, so means A times A times A. The rate of solute atoms jumping through one octahedral interstitial side to nearest octahedral interstitial side is R. So in specific directions, so they'll tell you gamma prime equals to R. So please answer solute diffusivity in terms of A and R. So you need to, based on the solute diffusivity in terms of A and R, so you can use the equation we derived from first sections. And we already know the gamma prime is, and now you need to know the Z and also small r. Then you can get the diffusivity, right? And for the F, interstitial diffusion, F equals to 1. So based on this, I need to know the Z, right? So let me draw the FCC first and highlight all the octahedral interstitial side expressed in white ball, small ball. Now the Z actually equals to, if you focus on this interstitial side at the center of this FCC, then you got 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So we got Z equals to 12. And the distance, the same, right? For this one is A over 2 square, A over 2 square, and A over 2 square, take the root on it. So there Z equals to 12. And R you can calculate equals to A divided by square root of 2. So you take all this information inside, then you got, after calculation, you got the diffusivity of these interstitials equals to RA squared. So the solute diffusivity already be expressed in as a function of capital R and A, as mentioned in the questions. Okay, so how about the question B? If we have assumed there's a solute concentration gradient along 100 direction is along x-axis, means there's a constant flux of solute atoms passing through these directions. Please derive the solute diffusivity in 100, the direction of 100 based on the net flux. So net flux tell you that you need to define two plane, alpha plane and beta plane, and know the flux from alpha to beta and beta to alpha and get the net flux, right? So based on this unit cell, we will assume this is alpha plane, this is beta plane. So based on previous check, first of all, in order to know the flux, you need to know the C-prime area density, right? So the area density of the interstitial side on alpha plane, we got a quarter, 4 times a quarter plus 1. So 4 times a quarter plus 1, and divided by the area is A times A, so we got 2 divided by A squared. So we got the C-prime. Okay, and next we are going to determine how many possible jump directions of the solute atom located at this interstitial side. So I'm going to use this enlarge figure to explain this possible directions. So now we have 4 octahedral interstitials at the center of the edge, right? So let's take a look. If this the solute locate at this side and want to jump to beta plane, it cannot jump directly to this corner, right? Because there's a atom locate here, so possible jump to here. So let me check. So I just draw more unit behind this and upper this. So I got this interstitial side in the meantime. So if I have a solute locate at least tetrahedral interstitial side, they can jump to beta plane to here, or down to the bottom or to the top. So there are 4 possible jumping directions to jump to beta plane. If I consider the other interstitial side at this corner or this center of the edge, also can be jump here, 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 and here, and the distance are the same, right? And if you compare this 4 jumping directions and this 4 jumping directions and find out actually this one is parallel and this one is parallel, so only 4 directions, jumping directions, right? And this is these 2 examples actually is we talk about the tetrahedral interstitials at the center of the edge. And how about the center of this cubic, this interstitial side? So take a look. This interstitial can also jump 4 directions to the front, back, upper, and down, lower location. And interesting, this direction is parallel with this and this. This one is parallel with this and this. So even there's 4 possible jumping directions to this solute atom at this interstitial side, but these 4 directions are parallel and identical with the others. So we only have 4 possible jumping directions, and each atom, because we have 2 atoms on the alpha plane, right? Each atoms, we have 2 atoms, and 2 of them can make a successful jump to beta plane. So we got 2 divided by 2 C-prime. So we got these results. And as we mentioned, in order to use a nav logs, so we want to modify the C-prime by C plus 8 over 2 partial C partial X. So use this 2 minus this 1, so we got the divisibility expressed like A squared R, the same with what derived in question A. Okay?